It was politician Ron Lewis who said, "It is never too early to encourage long-term savings." In this lesson, we're going to calculate the future value of a periodic deposit investment. We're going to graph the future value function, and we're going to interpret the graph of the future value function. All to answer the question, how can you effectively plan for the future balance in an account? Before we begin, let's make sure we're ready for this lesson by taking a look at warm-up number 2. Let's classify these exponential functions as decreasing or increasing functions. So f of x being equal to 5x, do you think this is increasing or decreasing? It is an increasing function. How about f of x is equal to 0.5 to the x power? This is a decreasing function. How about f of x is equal to 1.5 to the x power? This is an increasing function. Now, are you able to notice the relationship between the increasing functions as they compare to that decreasing function? Now, let's take a look at a problem that you will be able to do by the end of this lesson. Linda and Rob open an online savings account that has 1% annual interest rate, compound monthly. If they deposit $1,200 every month, how much will be in their account after 10 years? So we know our original formula, and their periodic deposits will be $1,200. The interest rate is 0.01, the time frame is 10 years, and it is compound monthly. So we substitute all of the values into the equation. We can then do 0.01 divide 12 equals plus 1 equals exponent 120 equals minus 1 equals times 1,200 times 12 equals divide 0.01 and hit equals. We get $151,379.85. Suppose you open an account that pays interest. You make no further contributions. You just leave your money alone and let the compound interest work its magic. The balance your account grows to at some point in the future is called the future value of a single deposit investment. A single deposit investment account is one in which no further deposits are made after the initial deposit. To calculate the future balance, use the compound interest formula on the screen, where B is the balance at the end of the time period in T years. P is the principal amount, R is the interest rate expressed as a decimal, and N is the number of times the interest is compound in 1 year. Many people add money to their savings account on a regular basis. The periodic investment is the same deposit made at regular intervals, such as yearly, monthly, bi-weekly, weekly, or even daily. Suppose Enrique gets paid every other week and has $200 directly deposited into his savings account. He wants to know how much he will have after 5 years. A common payment schedule for paychecks is bi-weekly, meaning every 2 weeks. In this case, Enrique makes an initial deposit of $200 and continues to make deposits bi-weekly for 5 years. Because he will get 26 bi-weekly paychecks per year, he makes a total of 130 periodic deposits, 26 times 5, each in the amount of $200. Had the account offered no interest, he would have at least 130 times 200, or $26,000 at the end of the 5-year period. The bank offers compound interest, so Enrique needs a different formula to calculate his balance at the end of 5 years. The future value of periodic deposit investment. B is equal to P times 1 plus R over N to the NT power minus 1, all in the numerator, all over R over N, where B is the balance at the end of the investment period, P is the periodic deposit amount, R is the interest rate expressed as a decimal, N is the number of times interest is compound annually, and T is the length of investment in years. Here, we're going to learn how to calculate the balance in an account in which periodic investments have been made at a given compound interest rate. Now, let's calculate the future value of a periodic deposit investment. Rich and Laura are both 45 years old. They open an account with Rhinebeck Bank with the hope that they will gain enough interest by their retirement at age 65. They deposit $5,000 each year into an account that pays 1.25% interest compound annually. What is the account balance when Rich and Laura retire? So the first thing is we have to remember what our whole formula is, and then we need to identify those variables where the amount being deposited periodically is $5,000. The interest rate is 0.0125. The number of times per year will be 1, and this will happen for 20 years. Why 20 years, you say? Because they want to retire at 65, and they are currently 45, giving 20 years to accomplish this. So the first thing we can do is substitute all of the values into the original equation. We would go ahead and multiply the exponent as 1 times 20, which is 20. This denominator at the moment seems a little inconvenient. So instead, we can multiply the numerator and denominator by the inverse of this, giving us all one nice, neat equation. To do this on a calculator like the TI-30XA, we would do 0.0125 divide 1 equals plus 1 equals exponent 20 equals minus 1 equals times 5,000 equals, we don't need to do that times 1, though if we had a different number we would do it, so we can say times 1 equals, but then divide 0.0125 and hit equals. We see that they will have $112,814.89. So let's check our understanding of this and find out how much would Rich and Laura have in their account if they decided to hold off retirement for 1 year. So we start out by knowing what our entire formula is, and you see here I've already inversed it into the numerator. Now when we substitute all of these values in and we calculate it in the same way we did in the example, we get that they have $112,814.89. We see that they have $119,225.08. Now this is what they get for having that 1 additional year. If we subtract what they got from just doing 20 years, $112,814.89, we see that that 1 year was worth $6,410.19. Let's carefully examine the solution to example 1. During the computation of the numerator, is the 1 being subtracted from the 20? And can you explain the reasoning? No, the 1 is not being subtracted from the 20. Using the order of operations, the 1 plus 0.0125 to the 20th power will be computed first. The 1 is subtracted from that value, not from the 20. How much interest will Rich and Laura earn over that 20-year period? Well, we already know that the balance in their account is $112,814.89. But how much money did they put in there? Well, $5,000 a year for 20 years means they themselves put in $100,000, meaning they earned interest of $12,814.89. Let's check our understanding of this, and using the example 1, check your understanding. How much interest would Rich and Laura earn by retiring after 21 years? Let's remember that that 1 additional year put $6,410.19 into their final balance, but they did pay $5,000 of that in, meaning their interest was $1,410.19. Linda and Rob open an online savings account that has 1% annual interest rate, compound monthly. If they deposit $1,200 every month, how much will be in their account after 10 years? So we know our original formula, and their periodic deposits will be $1,200. The interest rate is 0.01, the time frame is 10 years, and it is compound monthly. So we substitute all of the values into the equation. We can then do 0.01 divide 12 equals plus 1 equals exponent 120 equals minus 1 equals times 1,200 times 12 equals divide 0.01 and hit equals. We get $151,379.85. Let's check our understanding. Would opening an account at a higher interest rate for fewer years have ensured Linda and Rob have at least the same balance? Well, not necessarily. It would depend on the principal, the rate, and the length of time that these accounts were opened. Now, let's graph the future value of a function. Let's construct a graph of the future value function that represents Linda and Bob's account for each month. Use the graph to approximate the balance after 5 years. Having constructed the graph and understanding that the x-axis is not measuring years but months, they want to know about 5 years. And with 12 months a year, that means we're looking at 60 months. So at 60 months, we can approximate about $74,000. If we really wanted to see how good our graph was, we could substitute all of those values into the original function and find that B is in fact $74,000. To do this, we're going to have to set up the x-axis, which covers 20 years worth of months, which means we need 240 months in total. And we know that the value for that is going to go all the way up to $112,000. So we set the y-axis to $120,000. You'll notice I'm only going in number of tens, but the side shows that this is by the thousands. So this is not a 10, but $10,000. If at 20 years they had $112,814.89, that's approximately here. And we can simply draw the line in to see how that would look.